Okay, this is going to be the first of several videos that we're going to do to teach you how to do a chi-square goodness of fit test. Chi-squared or chi-squared goodness of fit test. It's a hypothesis test. We've done hypothesis tests for proportions. We've done hypothesis tests for means. This is going to be a hypothesis test that doesn't fit either one of those categories. But we'll talk more about that. First, let me give you a scenario where we could use a chi-square goodness of fit test. Let's say Fred believes there's an equal proportion of freshmen, sophomores, juniors, and seniors in his high school, and his teacher believes that the proportions are not all the same. To see if there's evidence that the proportions are different, his teacher is going to select a random sample of 60 students and conduct an appropriate hypothesis test. The appropriate hypothesis test here would be a chi-square goodness of fit test. So we're going to talk about when we use a chi-square goodness of fit test. When we have one sample and we are looking at our variable of interest is a categorical variable with more than two categories. If there were only two categories, we could use a one proportion z-test because we could figure out the proportion that fits in one category. That would give us the proportion that fits in the other. But this case, if you think about this, here is our data from our sample data. Oops, let's just make up some sample data. We don't have sample data. All right. Let's say that we took this sample of 60 students, and let's say that freshmen, sophomores, juniors, and seniors. Let's say we found 12 freshmen, 14 sophomores. Let's say we had 20 juniors. Let's say we got 60 altogether. So let's say 20, 14 is 34, 46. So we would need 14 more seniors to make 60. So these are the counts that we get from our sample. Let's just say I didn't do the sample. We're just using it as an example. These are the sample data. And Fred thinks that there's an equal number of sophomores, freshmen, juniors, and seniors. So what we would expect to see if Fred was correct is a proportion where all would be equal. If we did a random sample, we would expect it really close to 15, 25% in each of the four categories. We have one sample. We have a categorical variable with more than two categories. Our sample data, what we're also going to call, and what most people when we do this test, is our observed data. Is what we get when we take a sample. And our expected is the distribution we would have expected if our assumption was true. So when we have a case, we have one sample, categorical variable with more than two categories, we're going to look to see if the proportion fits, that's the goodness of fit, fits some assumed distribution, assumed proportions for each of our categories. That's when we're going to use a chi-square goodness of fit test. Let's talk about what the chi-square distribution is. It's a probability distribution like all the others we've studied, except this one, the chi-squared variable, takes on the value from 0 to infinity. But this is not a normal distribution like we have seen in the past in the other hypothesis test we did. This is normally a right skewed distribution. As the degrees of freedom, we'll talk about that in the next video. We'll talk about how to calculate the degrees of freedom. As the degrees of freedom get larger, then this hump in the chi-square distribution moves to the right and gets closer and closer to a normal distribution. But usually when we do this, we're going to have low degrees of freedom. As a matter of fact, in this test, we'll have 3 when we do this, but 3 degrees of freedom. And we're going to have a strongly skewed, right skewed distribution. And the horizontal axis is going to be the values for a chi-squared variable, which will end up in our test statistic. And just like in the other hypothesis test, we're going to get a chi-squared value of the test statistic. We're going to calculate that. And if it lands here, then the area to the right of that chi-square distribution is going to be our p-value. And we're going to compare that to some alpha, just like we did with the 1 proportion z-test, the 2 proportion z-test, the 1 sample t-test for mains, and the 2 sample t-test for mains. We're going to compare that p-value the same way we did with those tests to our alpha, and that's going to give us our conclusions. So this is what a chi-squared distribution looks like. Now, how do you calculate this chi-squared test statistic? The way that we calculate the chi-squared test statistic, the chi-squared value, your calculator is going to calculate when you run a test on the calculator, but you need to know how to do this. This is going to be the sum of each category, your observed data minus the expected for that category, that number, that difference squared, and then you're going to divide that by the expected value that you got. So in this case, for the test we're going to run, our chi-squared value would come from 12 minus 15 squared over 15 plus 14 minus 15 squared over 15 plus 20 minus 15 squared over 15 plus 14 minus 15 squared over 15. When we put all that in the calculator, we're going to get a number that's going to be our chi-squared value. And wherever that lands on this distribution, our chi-squared test on a calculator, we could also calculate with the chi-squared CDF menu, will give us the probability of getting a value that extreme or more extreme in this distribution. And that's our p-value. That's the probability of getting a chi-squared value for this expected count, this as extreme or more extreme than what we got. It works a lot like that. So mainly what I want you to see is what this distribution looks like, how we calculate the chi-square test statistic, and when to use a chi-square goodness of fit test. The next video, we're going to do all of the criteria for full credit when you run a chi-square goodness of fit test. When do you use it? When you have one sample, you're looking at a categorical variable that has more than 2 categories. That's when we're going to do a chi-square goodness of fit test.